Good morning, my dear NEET warriors. Welcome aboard to the Vedantu NEET English channel, the NCERT line by line series. And today we are going to complete the next chapter, chapter 6, Electromagnetic Induction. Okay, it's a very nice, sweet, and straightforward chapter. There are some nice new concepts over here. Faraday's law, Lenz's law, motional EMF and inductance. These are the only things which are there, and we will see it in a very depth, and we will see it line by line throughout this particular session. So welcome aboard, and today is also, like you can see, the thumbnail is very different. The last day of your Navratri challenge series. I know this lecture was supposed to happen on Saturday or Friday, but because of a lot of things happening around, I was not able to conduct it. So I thought I will take it off today. Okay. So after the lecture is over, make sure that you put down in the comment section, challenge done. The Navratri challenge completely done. All the days done. Right. So yes, I was traveling. I have not slept for last 2 days at all. And I have conducted seminars. MV-SAT was there. So you might see probably I look little bit tired, and it is natural that it is seen. Okay, so here I am, and again today evening I have some classes out there, but it is exam time and there are a lot of channels to handle, so let's do this. All right, so this is your Capto guys, working always for you. So get in all the kids out here for the Chapter 6, Electromagnetic Induction. And in case you have forgotten to smash the like button, do that right now and subscribe to the channel. Do not, forget that, because then you will not remember which video did I watch where, which channel was it, and all the important notifications, anything that comes up pertaining to you and your academics, it will be out here. Correct? Let's begin. Now, in this particular chapter, like you can see, there is some introduction. Let's understand what it says. Electricity, magnetism were separate for a long time. They were considered to be unrelated. In the early decades, experiments by Oersted, Ampere, etc., they showed that electricity and magnetism are interrelated. They found that moving charges produces magnetic field. An electric current deflects magnetic compass needle placed in its vicinity. The natural question arises like this: is the converse also true? Like, can magnetism create electricity? Okay, the answer to that was basically found by Michael Faraday's experiments in England and Joseph Henry in USA, which were in 1830. And they found out that electric currents were created in coils which were allowed changing magnetic fields inside of them. And we are going to study this particular phenomena where changing magnetic fields creates electric currents. This electricity which is generated is called as electromagnetic induction, this phenomena. And when Faraday made public his discovery that relative motion between the magnet and the loop produced currents in the coil, he was asked, what is the use of it? His reply was, what is the use of a newborn baby? And the phenomena of electromagnetic induction is not merely theoretical or academic interest, but of lot of practical use. Imagine a world where there is no electricity, no electrical lights, no trains, no phones, no personal computers. The pioneering experiments of Faraday and Henry have led directly to the development of all the modern day generators and transformers, and the whole civilization owes this progress to the great extent of the discovery of electromagnetic induction. Okay, I'll tell you. First of all, remember, people thought that electricity and magnetism were separate and unrelated. Like we have electric force, charges, they repel or attract. Magnets, they attract or repel. So one branch was electricity, one branch was magnetism. Even when you were a kid, you thought electricity is a separate topic, magnetism is a separate topic. Later on, it was proved that experimentally that the experiments on current, electricity by Oersted, etc., established the fact that electricity and magnetism are actually interrelated to each other. They are actually interrelated to each other. They are not separate. They are not separate. It was considered separate, but actually they are not separate. Like whenever you pass current through a wire, it produces magnetic field. It can affect magnetic coils or magnetic needles. Isn't that right? So we know even a charge which is thrown in a magnetic field, it gets affected by it and it will get deflected by a force F is equal to QV cross B. If you notice, Q is the branch of electricity, B is the branch of magnetic field. Both the things coming together was establishing the fact that electricity and magnetism are related to each other. It is like Pandu and Champa, when they got married, they were casually talking about their childhood. And you know what? In my childhood, when I was 14 years old, I had gone to see this nice place in Goa. Champa was like, yeah, you know what? Even I went to Goa when I was 14 years old. Then they were seeing through their pictures, Instagram, and then they realized, oh my God, we were at the same place at the same time. Oh, and you know what? I was there at that same restaurant, that same food festival was there. Oh, even I was there. Oh, wait a minute, you are there in my background picture. Hey, wait a minute, Pandu, I can see you in my background. So they found out they are related. So same thing happened with electricity and magnetism. Now, since electricity can produce magnetic field, current carrying coil can produce magnetism, current carrying wires can affect magnetic needles. The reverse, can magnetism create electricity? Can magnetic fields create electric field? Reverse. The answer is yes. So basically, if electric currents can deflect magnetic needle, the natural question is the converse possible. Can moving magnets produce electric currents? Such a relationship, is it possible? The answer to that is an astounding yes. It is possible. And that is what this chapter is all about. We will study this phenomena associated with magnetic fields in which electric current is created by changing the magnetic fields, and such an effect is called as electromagnetic induction. Now, Papa, this Faraday and Henry, they faced exact same lol movement, the complete, one palm face movement, same thing like what we or our kids, feel. Mom, Dad, you know what? I got first prize in drawing competition. Imagine your parents saying, so what will you do with first prize in drawing competition? What about mathematics? But I got first prize in mathematics. First prize in drawing competition. So, what about board marks? No interest only. Same thing Faraday Papa felt. Faraday, when he made his discovery that, hey, listen, I produced current inside a coil and I moved a magnet. People are like, so what? Like this they did. What is the use of this? His reply was, what is the use of a newborn baby? Got it? Understood? Yeah. So this is exactly what he faced during that time. So if you thought that your problems are just new, no, these problems have always been existing throughout our history. And a lot of people have faced this kind of criticism. So don't be bothered. Don't be bothered. I hope this is clear. Yes, Madhumati. Yes, Krishna. Hi, Janan. Jasmine. All right, Pratibha. Great. Hi, Suchi Mama. Nice to see all of you back over here. Great. So now that is what we are going to see, and all the modern day discoveries and things are basically we owe to Faraday and Henry. Yeah, that's what they say. Okay, fine. What are those experiments? The discovery and understanding of EMI, electromagnetic induction, are based on long series of experiments carried out by Faraday and Henry. We shall now describe some of these experiments. So, shows a coil connected to a galvanometer. When the north pole of a magnet is pushed towards the coil, the pointer in the galvanometer deflects, indicating the presence of electric field. The deflection lasts long as the bar magnet is in motion. Okay, what are the discoveries that he got? So, the galvanometer deflects, indicating the presence of electric current. The deflection lasts as long as the bar magnet is in motion. The galvanometer does not show any deflection when the magnet is held stationary. These are the observations, you should know it. The magnet is pulled away from the coil, galvanometer shows deflection in the opposite direction, shows deflection in the opposite direction, which indicates reversal of the current's direction. Moreover, when the south pole of the magnet is moved towards or opposite, the deflection in the galvanometer are now opposite, and further the deflection is found to be larger when the magnet is pushed towards or pulled away from the coil faster. Instead, when the bar magnet is held fixed and the coil is moved, the magnet is held fixed and the coil is moved towards or away, the same effects are observed. It shows that finally the relative motion between the magnet and the coil is responsible for generation. This generation is called as induction of electric current in the coil. Second experiment, bar magnet is replaced by secondary coil and a steady current is produced in that particular coil, and the coil is moved towards etc. the coil, another coil. It shows another deflection. This indicates electric current is induced. When this coil is moved away, again it shows deflection, but in the opposite direction. So basically the conclusion is the same effects are observed again in the relative motion between the coils that induces the electric current. So here the bar magnet is replaced by a secondary coil connected to a battery. So let's understand what and all is mentioned over here. So for that, we will just go to PHET, yes, and we will just go to electricity, magnetism and circuits. Okay. Now, see guys, we know that whenever you have a coil which carries current, see this is a bar magnet. See, this is a bar magnet. You can see this bar magnet, it produces a magnetic field. You can see a compass gets deflected around it. It shows that, there is magnetic field around it. Whichever direction it points, it shows that direction the magnetic field is there. And you can see the magnetic field lines are like this. If I make the magnetic strength stronger, you can see more field lines. If I make it weaker, it will be less number of field activity. Here the strength is more, here the strength is less. Okay. Now the same phenomena will repeat if I, instead of a permanent magnet, if I use basically an electromagnet. This is an electromagnet, basically a current carrying coil. Can you see the field is again exactly the same as a bar magnet. So current carrying coil produces a magnetic field around it. The magnetic compass deflects exactly the same way. If I reverse the direction of the current, the magnetic field also reverses. White becomes red, red becomes white. You would notice any point, let's say this one. White will become red, red will become white. Right? Because the direction of the current has reversed, so the field will also reverse. Okay. Fine, sir. Great. This is what an electromagnet is, sir. Okay. So what is the Faraday's experiment, sir? Okay. So let's go to Faraday's experiment now. So as per Faraday's experiment, what he did was, yes, let's have pickup coil, yes, over here. Okay, this is exactly a simpler version of Faraday's experiment. The actual version, the schematic, diagrammatic version in NCERT is shown over here. It's the same setup, guys, just I have shown it in a slightly different way. That's all. It's the same thing. Okay, observe now. What is there? There is a coil. Instead of a galvanometer, there is a bulb. What does a galvanometer do? It shows how much current is there. I can use a bulb also to see current is there, or I can use a galvanometer which shows the current. If it deflects this way, current is moving in one direction. If it deflects the other way, current is going in the other direction. No deflection means no current. More deflection means more current. Okay. What have I done? Taken a magnet. Right now the magnet is just kept over here. Is it showing any deflection? No. Which means, is there any electricity produced? Answer is no. I hope this is absolutely clear. Okay. So now what we are going to do is we are going to move the magnets. Now what we are going to do is basically we are going to move these particular magnets and see what happens. So if I move this magnet, oh, do you see? There is some deflection over here. And what do you see? The magnetic field in this region, is it not changing, guys? Is it not changing? So this shows that whenever the field passing through a coil changes, that produces electricity. A static magnetic field does not produce electricity. Changing field, right now the fields are stationary, it is not changing. But the moment I move the magnet, you can see the fields are basically changing. The fields are changing, so that is what produces electricity. So this was the main conclusion. Changing magnetic field through a coil, basically flux through a coil, when it changes, it produces electricity. Great. If I move the bar magnet slowly, the electricity produced is less. But if I move it fast, the electricity deflection, you can see, is also large. Okay, perfect. If I move the north pole towards the coil, then you can see the deflection is one way. If I move it away, it is the other way. Observe now. I'll move the north pole towards the coil, it deflected like this, left side. If I move it away, the deflection is right side. It shows that, the manner in which the field changes also decides the polarities, the direction of the current. So that was another thing. Also, instead of one turn, if I use 2 turns, the electricity produced will be double. Observe this. There is only one turn. I move this, it deflected so much. I move this, it deflected so much. Instead, I make 2 turns. Observe now. Wow, it deflected more. Wow, it deflected more. I make 4 turns. Observe now. Wow, so much of deflection. So much of deflection. So the deflection is proportional to the number of turns. More the turns, more number of times the field lines will pierce through the coil again and again. One coil, then second coil, then third coil. So you will see more electricity will be generated. So it is definitely proportional to that. Not just that, if I make the area small, observe it now, and if I move the magnet, so much deflection. If I increase the area, more field lines are piercing through the coil. They are entering through the coil. Observe, the deflection is more now. The deflection is more the moment the area increases. The moment the area decreases, the deflection is not so much. The deflection is not so much. So definitely it depends on the area. It depends on which polarity is going towards it. It depends on whether it is going towards or going away. It also depends on the number of turns. Can we move the coil? Yes. Even moving the coil will produce the deflection. I don't know whether you can see the deflection. Rather, I'll keep a bulb so that you can see it. Even if I move the coil, do you see the bulb is glowing? Can you see the bulb glowing, guys? Can you see the bulb glowing? So what does it say? Either the magnet moves or the coil moves. Either way, electricity will be produced. See this. See, electricity is produced. The bulb is glowing. So relative motion between the magnet or the coil, will produce electricity. This phenomena is called as electromagnetic induction. What a beautiful way to understand this. That was the first experiment. The second experiment was like this. Instead of a bar magnet, they used an electromagnet. Actually, wait. They used an electromagnet. Basically, they replaced the bar magnet with a current carrying coil. Don't you see this is behaving like a magnet? Yes or no? Keep it on the chat box. Did you see this current carrying coil is behaving just like our previous bar magnet? There is no difference. So the observation should be exactly similar. So if I move this, again you will see the bulb is glowing. Again you can see the bulb is glowing. If I even reverse the direction of the voltage, immediately the fields which are going like this now will go like this. So the flux through this will change. The field through the coil will change. Observe, it will glow. See, it is glowing. See, it is glowing. See, it is glowing. I will place it nearer so that you can see it very easily. See, why is it glowing? Because the direction of the current will change, field will change, the flux direction will change. So the current will be produced. Any flux change causes, any kind of flux change will cause electricity in it. And you can see all those previous observations. If I increase the number of loops, obviously the electricity produced will be also more. If I reduce the number of loops, I will see the electricity produced will be slightly less. If I decrease the area, then the electricity produced will be again less. If I increase the area, then I will see again the electricity produced will be definitely more. All those previous observations are still going to be valid. So that is what is basically explained in these two experiments. This was the first experiment. This was the second experiment. Is this absolutely clear? Two experiments clear? Write it down. Krishna, Madhumati, Tanuja, Jasmine, Suchi Mama, everyone. Absolutely. Very good. Third experiment. About two experiments involved in relative motion, magnet and a coil between the two coils. Through another experiment, Faraday showed that relative motion is not an absolute requirement. Shows that two coils C1, C2 held stationary. C1 is connected to a galvanometer while the second is connected to a battery. It is observed that galvanometer shows a momentary deflection when tapping the key is pressed. The pointer in the galvanometer returns to 0 immediately. If the key is held pressed continuously, there is no deflection at all. It is observed that galvanometer shows momentary deflection when the tapping of the key is pressed, and it returns to 0 immediately. If the key is held continuously, there is no deflection in the galvanometer. When the key is released, again a momentary deflection is observed, but in the opposite direction. It is also observed the deflection increases dramatically when the iron rod is inserted in the axis. Okay, so what was the third experiment? Basically, it is about this only. See, imagine it is 0 volts. You turn on the switch, meaning this circuit gets connected. The moment you turn it on, do you see there was a momentary deflection in the galvanometer? If you didn't see, I will show it to you again. Just one second. 0. Observe the galvanometer. Right now the circuit is off. I will turn it on. See, there was a small deflection. Maybe you could not see it so easily. I'll do one thing. I'll bring this closer. I will increase the number of loops so that you can see the deflection very easily. I'm turning it off. I hope you saw the deflection. I will turn it on. See, there was a deflection. I will turn this circuit off. Again, there was a deflection. I will turn this on. Deflection. But it goes off the moment it is on. Why? Because once the circuit is on, even the current is flowing, even though there is magnetic field, that magnetic field is not changing. That is why there is no current. But the moment I turn it off, see, there is a deflection. Why? Because suddenly there is a change in the flux. So, observe which direction does this galvanometer deflect. When I turn on this circuit, it deflected this way. When I turn off this circuit, it deflected the other way. It shows that again the current will reverse the direction when you do the exact reverse activity. Basically, when you turn on the current, the field might increase here. So the deflection might be, here. When you decrease the current, the flux is changing in the opposite direction. So it will deflect in the other way. So reversing the activity reverses the current, reverses the deflection. That is what is being noted down over here. Is this absolutely clear, my dear warriors? All the three experiments? Yes, perfect. So these were the three experiments. After this, you will never ever forget what exactly happens. Then they talk about magnetic flux. I will just block the results and I will just explain this once again to you. We have discussed about magnetic flux in the previous chapters also, which is BA cos theta. This is just a reminder of it. Faraday's, he called magnetic flux is defined the same way electric flux is defined. Magnetic flux through a plane of area of A placed in a magnetic field is given by this, where theta is the angle between magnetic field and the area. Okay. And if the magnetic flux has different magnitudes, different directions, then you do summation or integration. The unit of magnetic flux is Weber or Tesla meter squared. Magnetic flux is a scalar quantity. Okay. Here they are given these diagrams. I'll just remind you of this. Imagine you have, let's say, an area over here versus an area over here. Let's say here some magnetic field lines are passing through it. Here maybe more number of magnetic field lines are passing through it. Then I will say that this area is allowing more field lines, less field lines. So this is less amount of flux. This is basically more amount of magnetic flux, and this flux, this magnetic, B stands for magnetic flux, is given by B dot A. So it is basically your magnetic field dot producted with our area vector. Magnetic field dot producted with our area vector. That is your magnetic flux definition. More the field, more the flux. More the area, more the flux. Also angle matters. So what is the direction of this particular area vector, you might ask. So if this is the surface, the perpendicular drawn to it gives me the area vector, the perpendicular. If this is the surface, the perpendicular drawn to it gives me basically the area vector. So the angle between area vector and the magnetic field is basically theta. Area is a vector quantity when it is shown as a perpendicular to the surface itself. Perpendicular to the surface itself. Magnetic field is measured in Tesla. Area is measured in meter square. So that Tesla meter square is exactly a Weber. A Weber is nothing but Tesla into meter square. That's what they have mentioned over here. Now here the surfaces are flat, but what if the surfaces are not flat? Then what do you basically do? Say for example, and the field is also not uniform everywhere. Then you basically divide it into small areas, and you find the flux through each of such small areas, something like this. I'll just show it over here so that you get an idea of it. Imagine this is a curved surface, so area vectors at every point are in different directions. The fields might be also in different directions. So maybe I'll show some of the magnetic field lines over here, some random magnetic field line over here. So that magnetic field is B. That area vector will not be A, rather it will be dA. There will be some angle between them. Every point the magnetic fields will be also different. So the small flux, so the small amount of flux passing through that small area which I have considered over here, that small area, right, this particular small area which I have considered over here will be d phi, and that d phi will be nothing but the magnetic field dot the small area vector. So therefore the total flux phi will be integral of d phi. Integration means summation, that means addition. Therefore that total flux will be integration of our magnetic field dot area vector. Our magnetic field dot area vector. Is this absolutely clear? How we find the total flux for a curved area for random magnetic field? Everyone, you understand why integration came instead of summation? Because integration is just like summation but for small quantities, for small things. Great, that is what they have explained over here. Alright, so let me just block this also. If the magnetic field has different magnitudes and directions at various parts, then the entire thing is given via basically integration. Okay, great. So that was this particular slide. Moving on to the next slide, guys, coming up on your screen. Okay, now Faraday's law of induction. Faraday arrived at a conclusion: the EMF is induced in the coil when the magnetic flux through it changes with time. So what was the conclusion? Faraday arrived at a conclusion that EMF is induced when there is magnetic flux which is changing, and all these were supported by his observations during his experiments. So all those experiments, observations are mentioned over here. All right, and from that from that, he creates a final formula. All the experimental results are mentioned in this particular paragraph. No need to memorize this. There is nothing important there. Whatever I showed you, right, the same things are mentioned over here. Okay. The Faraday's law is stated as Faraday's law of electromagnetic induction. Faraday's law of electromagnetic induction, which says that the magnitude of the EMF is equal to the rate of change of the flux through the particular circuit, and the formula for this is exactly this one. EMF which is induced is d phi by dt. I'll come to it, why minus sign. Just to show you what they have written in this paragraph, he says that the faster you move the coils, more the number of turns, what happens? You can see more field lines will pass, or more field lines will change within this coil in which electricity is generated. So, how quickly the flux changes decides how much deflection or how much electricity is generated. If it is not changing so much, then the electricity generated is also not so much. But if it changes really fast, then the electricity generated is also more. So flux change, how quickly it happens, decides the electricity which is generated. Electricity generated, the other word for it is electricity induced. But you need to measure it with something, either amperes or volts or something. So we measure it in voltage, volts. So the electricity generated is called as the EMF which is induced. Why the word EMF? Because see, there was no battery connected to this, but me moving this coil has created electricity in it, so it is behaving like a battery. It is behaving like a battery. Just the main difference is, in a normal battery, chemical energy in the battery gets converted into electricity. Electrolytic elements are there which generates electricity. Here it is generated because of the phenomena of induction. This coil is inducing electricity in it. This coil is moving electricity in it. Yeah. So it is like Pandu, guys. This coil, no, is like Pandu. This coil is like Champa. This Pandu is where the electricity will be generated. This Champa, if she is standing over there, Pandu is not getting entertained. No entertainment. See, Pandu, is he getting entertained? No. Champa moves. She dances. She dances. So then this coil will also get entertained. This coil will get entertained. Wow, very nice. Champa stops? No. Champa dances faster. Tak, 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 dang, ding, dang, 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 doom. That's it. The coil will get entertained. So that is exactly what is happening over here. So that's what Faraday also says. The observations in the form of the Faraday's law of electromagnetic induction, the magnitude of the EMF induced in the circuit. This is our Pandu. The magnitude of the induced EMF in a circuit. So Pandu's entertainment is proportional to how quickly Champa is changing the flux. How quickly there is rate of change of magnetic flux in the circuit. Understood, guys? So this is Pandu, this is Champa's dance. Champa is at rest, phi will be constant. Champa is just like this. Pandu is like, what are you doing, Champa? Change. So Champa dances. So Champa dances. So d phi by dt. d phi by dt will come, EMF will be induced. EMF will be induced. Pandu will get happy. Wow, very good, Champa. Champa dances fast. Pandu will be like, wow, very good. That's what happens. Why this minus sign? We'll come to it in a later on point. It is because of Lenz's law. Okay. So, before going there, let me talk about this N first. If there are N number of turns in that secondary coil, obviously you will see that more EMF will be generated because more flux will pass. So this N will come only for the sake of showing that there are more number of turns. So I'll just mention that in the case of a closely wound coil of N number of turns, the flux will be also, at a higher value. So the induced EMF will be increased by the number of turns. Hence you multiply N with it. Hence you will multiply N with it. Very good. Everybody understood. So everybody needs a Pandu and Champa in the life to understand any kind of complex law in physics. What is that negative sign? Let's talk about that negative sign. The negative sign indicates the direction of the EMF and hence the direction of the current in a closed loop. This will be discussed. See, they are also saying we'll discuss this later. Okay, we'll discuss this later. Anyways, now the flux can be also altered by changing the shape of the coil, rotating it. In these cases too, EMF is induced. All right. Okay. So how can you change the flux? Observe this. See, if I want EMF to be induced, that means I 100% want the magnetic flux should change. Only then EMF will be induced. How can I change the magnetic flux? There are only three different ways. There are only three ways by which I can do it. What are those three ways? Observe. First way is, imagine my magnetic field only changes. Magnetic field changes. Meaning, imagine I bring the bar magnet close to it or away from it. So magnetic field changes. So this way flux will change. And this is exactly what we have been seeing over here. I bring the magnet close or far away, EMF is induced because the field passing through it is definitely changing. The flux is changing. So now it is becoming strong, now it became weak. Now it became strong, now it became weak. So flux change definitely causes the EMF to be induced. The second option is because flux is B into A into cos theta. I can change B, I can change A, or I can change theta. So next is changing the area. So the next is basically area itself changes. Imagine guys, there was a coil like this. It is held like this. Now it has some area. Now imagine I do this. Area has increased suddenly. Area has increased. I do this. Area reduced. Imagine this. I make it like this. Area reduced. Now area increased. So imagine magnetic field lines were passing through it. Okay. Now there is less flux. I make more flux. Less flux, more flux. Won't electricity be generated in this? Obviously. So changing the area also will change the flux, hence creating electricity. The last thing is basically changing the theta. Theta changes. Theta basically changes, which makes sense. The coil was like this, I change the orientation, change the orientation, change the orientation. Immediately you will see electricity will be generated in it. Is this absolutely clear? That is exactly what has been mentioned in this particular paragraph. That is exactly what is mentioned in this particular paragraph. Shall we now start seeing some questions, guys? That will be better. Okay, so let's see. There is a square loop of certain side and resistance. It is placed in the east-west plane. A uniform field is set up across the plane in the northeast direction, north to east, not northeast, north to east. Magnetic field is decreased to 0 in 0.7 seconds as a steady rate. Determine the magnitudes of the EMF and etc. All these things. They have done the calculation. So basically, let's understand what is this. First, let me place my coil. This is our coil, guys. This is our coil like this. It is vertically. It is in the east-west vertical plane. The magnetic field is in the northeast, my bad. It is slightly different. North to east direction, the vertically in the east-west plane. Okay. So basically it means this is our east, this is our west, this is vertically upwards, this is vertically downwards. If you go inside, it is north. It is north. If you go inside like this, that is basically your north direction. If you walk inside the plane or towards the board. Okay. Now, if you look at it from the top view, the same thing, that coil's only top part will be seen. And then you will realize, okay, this is the north direction, this is the east direction, this is the east direction, this is your west direction, and obviously like this towards you will be basically vertically upward, and down will be over here inside the plane of the board. This is basically your top view. This is basically your top view. Are you able to visualize this coil first? Yes or no? Give me a thumbs up. Are you able to visualize this coil? Hi Disha. Yeah. If you are able to visualize this coil, then you will be able to do it, because otherwise whatever they have done over here, right, will be very, very difficult to understand. Where is the magnetic field? The magnetic field is in the northeast direction. I cannot show it here so easily. It's a little difficult. This is north, this is east. So the magnetic field is actually going at an angle, guys. The magnetic field is actually going at an angle northeast direction. So basically this angle which you are seeing over here is nothing but 45 degrees. And if you talk about the area vector, this exactly is our area vector, perpendicular to the plane. So area vector is actually inside. Area vector is inside. So when you see from the top, you will see it sticking outside like this. So this north direction is our area vector. So the angle between area vector and the magnetic field is 45 degrees. Is this clear, everyone? Visualizing this? Okay. So now, as per this, you can see that the field is set up across the plane. The field is decreased to 0 in 0.7 seconds. So if you talk about initial field, it will be magnetic field into area into cos theta. Magnetic field will be given, I think, 0.1 Tesla. Area of the coil, square of loop side 10 centimeter. If the loop side is 10 centimeter, what will be the area, guys? 0.1 meter into 0.1 meter, which is 0.01 meter square. So put the area as 0.01 meter square. Cos theta, it is cos 45 degree. What is cos 45? 1 by root 2. So this will become 10 to the power minus 3 by root 2 Weber. That is your initial flux. What about the final flux? What is the final flux? It is decreased to 0. That means no field only, 0, nothing. So definitely it has changed. Can you see? There is definitely change in flux. There is change in the flux. How much time it took? 0.7 seconds. So 100% there will be EMF induced in it. And the induced EMF magnitude is, how much is your change of flux upon the time taken? Why is there no minus sign? Because here there was minus sign. I am just interested in the magnitude, the modulus. So I'm not worried about the sign. I've put mod symbol also. How much is the change? This minus this. So basically 10 to the power minus 3 by root 2 minus 0 upon, how much is the time taken? 0.7. 0.7. Is this absolutely clear, guys? Yeah, and in ideas, I'll come to the EMI lesson also on the JE channel. Don't worry. Yeah. Now, actually speaking, this 10 to the power minus 3, 1 by root 2 is actually 0.7 approximately. So you will see approximately it is 10 to the power minus 3 volts, which is basically 1 millivolt. You can see approximately it will weigh 1 millivolt. Yes, it is correct. Approximately 1 millivolt of electricity is generated in this coil because you removed the magnetic field. Now the another question is also there, which is about current. How do I find the current? Guys, the current which will be created will be the EMF which is generated divided by the resistance of that particular coil. Oh, Ohm's law, E is equal to IR. I will be E by R. So EMF is 1 millivolt. Resistance, is it given? 0.5 ohms. 1 by 0.5 is 2. So it will become 2 milliampere. So the current which is induced is approximately 2 milliampere. I hope this is absolutely clear. Yes. Everybody? Now some of you will be like, sir, what about the Earth's magnetic field, sir? Why is that not considered? Can somebody tell me the answer in the chat box? Why did we not consider the Earth's magnetic field while making these calculations? Can anybody tell me in the chat box? There is a reason for that, and the reason is it was never changing. It was always constant. Yeah, so that's the reason for it. So the Earth's magnetic field is also producing a flux, but it is a steady field which does not change with time. Hence, it is not going to be considered. It is not going to induce anything. That's the reason for it. Next, there is a coil of some radius, 500 turns, some resistance. In its perpendicular plane, there is a horizontal component of the Earth's magnetic field. It is rotated, theta is changed by 180 degrees in 0.25 seconds. Estimate the magnitude of the EMF and the current which is induced in the coil. Horizontal component of the Earth's field is given to be 3. There is a circular coil, these many turns, this many ohms. In its plane is perpendicular to the horizontal component of the Earth's magnetic field. Okay, let's understand what exactly is happening. This is the coil. This is the coil, guys, simply put. This is the plane of the coil. The plane of the coil with its plane perpendicular to the horizontal component. Okay, so I need to take, oops, I can't do that. So think of this as your area vector. The plane of the coil is perpendicular to the horizontal component. Horizontal is like this. This is horizontal. This is vertical. So this is the Earth's magnetic field which is given to me. The Earth's horizontal magnetic field, which is 3 into 10 to the power minus 5 Tesla, that is given to me. Now what is done is this coil, I hope you understood, this coil is basically having its plane which is perpendicular to the horizontal component. So the area vector will actually be in this direction only. Area vector is parallel to the Earth's magnetic field. Now what you do, you have rotated the coil by how many degrees? It is mentioned 180 degrees. So which means that coil will now be basically like this. The area vector is now right like this. This is where the area vector is. Obviously the Earth's magnetic field is still, in this direction. There is no change in that. So in this process, theta has changed. Theta has changed. The angle between area vector and the magnetic field has changed because the coil was turned by 180. So the area vector also has turned by 180 degrees. So obviously flux change has happened. So let's calculate the initial and the final flux, and then we can find the magnitude of the EMF and everything else. If you ask me, what is the initial flux? I'll be like, it is BA cos 0. What is cos 0, guys? Cos 0. Why 0? Because it is 0 degrees. Cos 0 is 1. Magnetic field is already mentioned. 3 into 10 to the power minus 5. What about the area? Radius is given to be 10. Turns is 500. Oh, so I also need to multiply it with the number of turns, or else I will be making a mistake. So pi into 0.1 square multiplied by 500. Very, very important. Pi r square is the area into 500 because there are n number of turns. So each turn will create that flux. So into n also needs to be done. Okay. 3 into 5 is 15. Pi as it is. 10 to the power minus 5, 10 to the power minus 2, 10 to the power minus 7. And these two zeros, actually they will cancel. So into 10 to the power minus 5 Weber. That is your initial flux, guys. If you ask me about the final flux, it will be B A cos 180 degrees into n. So the same thing but with a minus sign, because cos 180 is negative. So it will be minus 15 pi into 10 to the power negative 5 Weber. So that is your final flux. So definitely there is a change of flux from positive to negative. So that change will produce that electricity. So let's go to the EMF which is induced. The EMF which will be induced, which is that change in the flux upon the time taken. I'm only interested in the magnitude. This minus this, guys. So 15 pi minus 15 pi. That's the change. The whole thing into 10 to the power minus 5. Whole thing divided by the time taken. Time taken was 0.25 seconds. 0.25 is 1 by 4, so 4 goes on the top. 15 pi minus minus becomes plus, so it will become 30 pi into 10 to the power minus 5. 4 3s are 12, 1 0 will go, so 12 pi into 10 to the power minus 4 volts. That is the answer for the EMF which is induced. If you want, you can also find the value of it. So it should be basically 12 pi, which comes out to be 3.8 something, 3.8 into whatever, yeah, 10 to the power minus 3. Is this absolutely clear, guys? Yeah, 12 pi into 10 to the power minus 4. Once I get the EMF, finding the current is not that difficult. The induced current will be the induced EMF upon the resistance of that coil, which is 12 pi into 10 to the power minus 4 volts by the resistance, which is 2. So it will be basically 6 pi into 10 to the power minus 4 amperes. That is your induced current. That is your induced current, EMF by R. That's it. Clear, guys, how to solve these kind of questions? Main problem was N. Many people forget the number of turns. If you forget N, everywhere that factor of N will give you a wrong answer. Everywhere. Second thing, angle between the area vector and the magnetic field. If you make a mistake there, again another problem will happen. If you think it was perpendicular, sir, it was perpendicular, angle is 90 degree. Cos 90 will give you 0. The answer will be 0 then. So we will make another mistake. So the plane of the coil is perpendicular, but area vector is perpendicular to that also. So ends up being parallel. Area vector ends up being parallel to the field. That is another common mistake. Diamond clear? Very good. Awesome. Clear. Perfecto. Hi, Virat Vishnu. Welcome aboard. All the new students who are watching the class, make sure you are commenting, liking, subscribing to the channel. So you have seen all the ways, guys, how magnetic field changing, area changing produces. Here the magnetic field changed. In this question, the area changed. How it produces, electricity. What about theta change? We'll come to it towards the end. Don't worry. Theta changing concept will come towards the end. Lenz's law. Basically, this is going to talk about the negative sign. Remember, I have told you we'll discuss it later. I told you that we'll discuss why that negative sign comes. The negative sign, it will be discussed later. So now is that later time. So Lenz's law says that how the direction of the current is decided. Yeah. Hi Nitish, thank you so much. I hope you too have a very, very bright day. Thank you so much for such a lovely wish. And all the warrior Pandus lighting up the chat box. Jasmine, Madhumati, Krishna. Thank you so much, guys. Thank you so much. Okay. So, oh yes, Krishna will have water. Thank you. Okay, now the direction was given by Lenz's law, the direction of the current. Lenz's law gives the direction of the EMF and the current. The polarity of the induced EMF is such that it tends to produce a current which will always oppose the change in the flux produced in it. Negative sign just shows that particular effect. That negative sign actually shows this particular effect. We can understand Lenz's law by examining experiments, etc. And to counter, they have explained it. I will explain this to you, don't worry. Now consider the wire magnet will be attracted. This violates the law of conservation of energy and hence that cannot happen. Okay, this dissipate by as per the Joule's law of heating. Okay, and then they have given one example over here. Okay, so let me bring back our experimental setup. Let me bring back our experimental setup back over here. Now, as you can see, my dear warriors, over here, this bar magnet right now is not creating any electricity over here. Which direction will the current flow is decided by how which polarity is moving in which direction. Right now the north pole is coming towards the coil. You can see a current is created in this particular coil. As you can see, as I move this bar magnet, a current is created in this coil. If I move it in the opposite direction, the reversal of current happens. The reversal of that particular current, definitely it happens. I'll increase the loops so that you can definitely see it very clearly. So, how is this current direction decided? See, imagine when I move this bar magnet, there is a current moving in this coil. This current will also create a polarity. This current will also create a magnetic effect. It will produce its own magnetic field. Not this, guys. This current will have its own magnetic field. This will also behave like an electromagnet. Agree or disagree? Me moving this, there is a current which is created. So naturally what will happen? There will be a north-south, south-north polarity which will be created because of this coil only, this coil's current. Right now there is no polarity because there is no current, but when I am moving it, while I am moving it, there is magnetic polarities which are created. How will that polarity be? Just imagine, when I am bringing this magnet close, if there is a south polarity here, north polarity here, this is south, this is north. Will this magnet be attracted or repelled? Put it up in the chat box. When I am bringing this magnet close, if there is a south polarity here, north polarity here, south here, north here, what will this electromagnet do to this permanent bar magnet? Tell me, will it attract it or will it repel it while I am bringing it close? What do you think it will do? It will attract it. Yes, correct. South attracts north, south repels south. Everybody, very good. Which means, imagine if I push this magnet will get attracted by this coil. If this magnet gets attracted by this coil, won't this guy's kinetic energy increase? Won't this getting attracted increase its kinetic energy? Wow. At the same time, electricity is also getting generated. So electrical energy is being generated, kinetic energy is getting increased. Who is giving this energy? Think, is Pandu giving? Is Champa giving? Is some bond being broken? Is something else happening? The answer is no. From nowhere, you are creating kinetic energy and electrical energy. This is violating the principle of conservation energy. This should not happen. Hence, whatever we assume is incorrect. So actually what might be happening is, when I am moving it over here, the north polarity is created here, south polarity is created here. What will north do to north? What will north say to north? Why are you coming? Repel. So it will decelerate it. It will, this coil, this magnet which was moving fast will start slowing down. It will start slowing down. Earlier it was moving fast, now it will slow down. So where is the kinetic energy going? That kinetic energy is going into this coil's electrical energy wirelessly. Imagine wirelessly energy getting transferred to something else. That's the beauty of electromagnetic induction. Got it? Everybody with me on this? Absolutely clear. So the polarities of the coil in which electricity is induced in such a way that it always will oppose the change. It will always oppose the change. Right now, while I was bringing this magnet here, there was a north created here, south created here, asking the magnet to stop. But if this bar magnet is going away, then current will also reverse, meaning the polarities will reverse. So when I take this bar magnet away, you will see a south polarity will be created here, north will be created here. What will south say to north? Come to me, come to me. Yes, so as you push this magnet away, it will start slowing down, it will decelerate. Again, the kinetic energy gets transferred into the coil's electrical energy. Again, the kinetic energy is getting lost and converted into electrical energy, which obeys our principle of energy conservation. This is exactly what happens. So, looking at this behavior, it feels like, sir, you know, my elder brother and sister, sir, anytime I want to go out, no, they will be like, no. Why are you going out? Stay at home. Sir, when I tell, today I am going to stay at home and enjoy my day, then my brother and sister, why are you staying here? Go out. I want my friends to come over here, you get out of the house. What is this, sir? Whatever I do, every time opposition, sir. Today I thought I will sit and study. I got one nice scolding, sir. Why do you want to sit and study today? Go out and play. What is this? If I say that today I want to go play with my friends, no, you come sit and study. Every time opposition, whatever I do. If I say I want to dance, don't dance. If you say I don't want to dance, dance. So this is exactly what Lenz's law is. If this magnet comes here, this coil will be like, why are you coming close? North pole, North pole, North pole, repel. Okay, it stops. If this goes away, South pole. Oh, come. Why are you going away? So, you know, every time the behavior is to oppose any kind of change. If it tries to increase, it will try to decrease it. If it tries to decrease, it will try to increase it. Always oppose. Always oppose. That is exactly what Lenz's law is. Else, it would violate the conservation of energy. Else, it would violate, this would violate the conservation of energy, which cannot happen. So, Lenz's law is based on the conservation of energy principle, nothing more. And that is exactly what you should understand. So, let's try to see some examples over here. Let's try to see some examples over here. Shows the loops of different shapes moving in or out of the region of a magnetic field which is directed into the plane. What are these crosses showing? Magnetic field. Where is it going? Cross means going away from you inside the plane of the board. Dot means it is coming towards you. Okay. So, this coil is coming in, this coil is going out, only this much region is magnetic field region. This coil is again going out. All right. Fantabulous. So, oh, thank you. Yes. So, let's shade the region where the flux is present. Here. Oops. Whatever region I am shading, that is where the flux is right now present. Later on, that will also change because they are going either in or out of that zone. Are you able to see that? Are you able to see that regions which I have shaded, guys? Okay. Great. Determine the direction of the induced current in each thing. Tell me, as this rectangular loop comes in, will the flux increase or decrease? Tell me clearly, guys. Will that flux, because now as soon as it comes in, this much part will also be inside. So, won't the flux increase, guys? If the flux increases, but where does it increase? It is going inside. The flux increases inside. What will Lenz say? Why are you increasing? I will try to reduce you. So, the induced magnetic field will be opposing it. Induced magnetic field will be towards you. The induced magnetic field will try to weaken it. It will try to weaken. It is trying to weaken it. Because it is increasing inside, it will try to weaken it. Now, if the magnetic field line is coming towards you, take your thumb, put it towards you. See how the fingers are curling. See how the fingers are curling anti-clockwise. So, the current in this particular coil will be in this anti-clockwise direction. So an anti-clockwise current is being induced over here. Is it clear how Lenz's law has to be used? It's very simple. See whether it is trying to increase or decrease. Oppose that change. That's all. Absolutely. Let's go to this one over here, or even this one. Tell me, as this or this coil is trying to go away, next instant the flux will only remain in this much part, because this much part would have gone out of the field. So in these two, what is happening? In these two, what is exactly happening? Obviously, the flux is decreasing. The flux is decreasing inside. So because it is decreasing, what will the induced field say? What will the induced field say? The induced field will be like, wait a minute, I will support you. I will strengthen you. I will strengthen you. Strengthen you means field should be inside. Field is inside, take your thumb, put it inside the plane of the board, see how your fingers are turning. Clockwise, guys. So you will see a clockwise current which will be set up inside. A clockwise current. Even here, the induced current will be in the clockwise direction. So, yeah. Current flows along BACB, and here also the same thing that they have mentioned. Now magnetic flux decreases, okay. There are no induced EMF as long as the loops are completely inside or outside. Okay, there is one peculiar case which I want to discuss. Tell me what would happen if I made another new loop over here. If I made another new loop over here, and this loop is traveling here. Tell me, guys, in this particular loop, which direction will the current be induced? It's completely inside. Because it is completely inside, you know what happens? Whether that loop is here or just after some time, maybe that loop reaches over here. Just maybe after some time, the loop reaches here. Tell me, has the flux changed? Tell me, has the flux changed? No, right? So basically, that flux, for that, the flux is constant. The flux doesn't change. So because of that, what will happen? Induced current will be also zero by Faraday's law. There will be no current only. That is exactly what they have mentioned here. If there is the loop is completely inside or outside, then there is no current which is induced. If there is no current, that means the loop is completely inside or completely outside. It is not entering in or nor is it exiting out. Okay, very, very important conclusion. Great. Now that we have studied till here, let's go to the next part, which is basically your motional EMF. Motional EMF. Here, I'll explain to you very simply, in a very easy manner. There is a wire which is bent in the form of a C shape. This is the alphabet C. This also looks like C. So imagine you take a long wire and you bend it in the form of C. So that is why it is called as a C-shaped wire. On that, you take a rod and such that it is touching at both the points on the C-shaped wire. There is magnetic field also in this region. Okay. Now what happens is, imagine this rod is here. So if you measure this particular area, this is the area which will give me flux within this coil. This is like a coil. There is some flux passing over here. After some time, just imagine this same rod reaches over here. This is after some time. Okay, just after some time, the same rod maybe reaches here because of some motion, because of some velocity. So what will happen now? What will happen now? If you measure the flux, it is only through this much part. It is only through this much part. Can you see this much part has gone away? So definitely this part corresponds to the change of flux. Change of flux. And what does change of flux give you? If there is a change of flux, there is definitely EMF which is induced. And why did this happen? This happened because of the motion of the rod, motion of a conductor, motion of a conductor. So a moving conductor in a magnetic field created electricity, generated electricity. Hence the name given motional EMF. Motional. Due to the motion, there is EMF. Hence motional EMF. Is this absolutely clear? Everybody? Okay. That is exactly what this is. So they have mentioned it over here. The value of this EMF, that is the main formula which you should know. Derivations and all that not needed at all. So the value of the induced EMF is given by magnetic field into length of the conductor into the speed. Magnetic field into length of the conductor into the speed, the velocity. So the induced EMF BLV is called motional EMF. We are able to produce EMF by moving a conductor in a magnetic field. In a magnetic field. I hope this is absolutely clear. Everyone? Okay. So, imagine this. This explanation and all that is not needed. Don't worry about it. I'll explain it to you in a bit. Don't worry. Imagine this is the axle of a vehicle. This is the wheel. This is the wheel. Okay. It is going on a road. It is just going on a road. Imagine Earth's magnetic field is there and Earth's magnetic field is like this. This is the Earth's magnetic field. This is your wheel. This is the axle. And the axle is having some length L and it is moving with some speed. Don't you see that axle, since it is moving with some speed, between the ends of the axle, there will be some EMF which is generated. That EMF which will be induced in that particular axle will be given by B into L into V. If you measure approximately Earth's magnetic field is of the order of 10 to the power -4, -5 Tesla. Let's take a slightly stronger point. Let's take 10 to the power -4. Length, maybe it is around 2 meters. Maybe you are going with 20 meters per second. Okay, this is 2 meters. This is 10 to the power -4 Tesla. This will become 2 2s are 4, 0, and this will make it 10 to the power -3. So which is around 4 millivolt. So imagine when you are driving a car or a truck, imagine between the two tires of the truck there is a electric voltage which is created, EMF which is developed, but it is very small. 4 millivolt is not much. 4 millivolt is not too much. You need a very long axle or you need very large speed so that you can create enough electricity. Sir, what about bullet train, sir? Sir, bullet train will go, or sir, what about a jet, sir? Fighter jet. Fighter jet has a long wing, and it has got, large speed also. Will the electricity generated in that be more? Yes. So instead of 2 meters, make it 10 meters. Instead of 20, make it 100 or 200. So you can see it will increase by a factor of some, 100 times or something like that. So instead of 4 millivolt, it will become 400 millivolt. Still it is 0.4 volt. It is not much. It is not much. So you can see the EMF which is induced is there, not much, but it can create some undesirable effects in some places. Trisha, no issues. Watch the recorded class because we had a lot of fun today, lots of animations and simulations for visualization purpose. Okay, watch the recording. All those who are joining in late, no worries. Yeah, but please make sure that you watch at least the recording. Okay, don't miss the class. It's a very interesting class. So electricity is created even in a moving train, moving axle, fighter jet because of the earth. So, this gives weird ideas. So, I can generate electricity from moving objects, and that's exactly what happens while you are trying to generate electricity in a generator, in a hydropower plant, in a nuclear power plant. They use moving coils, moving conductors to generate electricity. Another such example is of a rod which is rotating, not translating, rotating in a magnetic field. Imagine I take a rod and I'm rotating it like this. Then how much electricity is being generated inside of this? How much electricity is being generated inside of this? So this is a very important derivation which you should know. Imagine you take this conducting rod whose length is basically L, and it is known to me that it is in a region of magnetic field like so. This is the region of your magnetic field. This rod is rotating, it's hinged over here. It is rotating like this with an angular speed omega. Now what happens is, in this particular diagram, you will see every point has a different velocity. So here the speed is less, here the speed is more, here the speed is even more, here the speed is even more. So the EMF generated will be also different at different points. If you take a small section of that rod, okay, if you take a small section of that rod which is at a distance of x, whose width is dx, whose velocity is v, there is a small EMF which is generated in it. I will call it dE. There are many such things, so think as if there are many batteries till the end. Many batteries till the end. From the start till here. So this rod is small EMFs arranged in series. So this rod altogether will behave like one single battery whose EMF induced is E induced. And the question is, how much is this E induced? That is what we need to find. So obviously there is integration over here which is involved. If I find D, my job is done. But to find that, I need to know the speed. By circular motion, we know velocity, radius and omega. They are related. So V will be nothing but omega into x. V will be nothing but omega into x. Omega r, so omega x. That small EMF which is generated, the EMF induced in the element, in that particular element, using the formula BLV, L is dx into V. So it will be B, velocity was omega x and dx over here. That is your dE. But I don't want dE, I want the total EMF. The total EMF will be integration of all this d. The d is nothing but b omega x dx. So I have to integrate this to get the total EMF. B and omega are constants, only x and dx will remain inside starting from 0 to L. X starts from here when x is 0. When x goes till here, the value of x is the length of the rod. So integration of x with respect to dx is nothing but x square by 2. So it will become L square by 2 minus 0 square by 2 after putting the limits inside. So it will become b omega L square by 2. That is the induced EMF. That's exactly the formula which you need to use to solve this particular question, guys. B omega L square by 2. If you substitute omega, substitute field, substitute the length, you will get it. Okay? I hope this is absolutely clear. Absolutely clear. Everybody with me? Okay? Perfect. Now there is one important point which is mentioned over here. Let me stress on it a little bit. If there are more spokes, then what will happen? So imagine there is one conductor here, another conductor over here, Okay, imagine these are the conductors and all these three conductors together are rotating like this. There could be 4 or 5 also, doesn't matter. Then will there be EMF generated across every one of them? The answer is yes. Every part of that rod will behave like an independent conductor. EMF induced in each of them will be half B omega L square. Same EMF here, same EMF here also. So now, if you measure the EMF across this point and this point, this point and this point, this point and this point, each of them will behave like a battery but in parallel. Yes, understand this. Very, very important, guys. Each of them will behave like a battery but in parallel, like this. This is your common point. This is your common point, and all these outer points, you can think of them to be at the same potential, guys. Very, very important. So it's like all these outer points are at the same potential. Perfect. So therefore, they behave as if they are in parallel. They behave as if they are in parallel. This point, this point, this point. They are all connected as if, you know, at the same voltage. So they are in parallel. So hence this diagram will be as good as saying you just have 3 batteries like this. And when batteries are in parallel, they behave like a battery in this particular manner. Same EMF, same EMF. So once they are in parallel, the EMF does not increase nor decrease. It will be the same. There is no difference at all. Okay, it's just that the internal resistance will be different. If this has an internal resistance R, and R, they are in parallel. This internal resistances are in parallel. So internal resistance will become R by 3. Internal resistance will become R by 3, but EMF will still remain E only. There is no difference in that. Is that clear, guys? Everybody? So that is the meaning of this last statement. You might get a question in NEET also or in boards also based on this particular concept. Very, very important. Clear? Shall we go ahead? Okay, perfect. Now let's come to inductance, because this is the last part, inductance and your generation. Inductance and your generation. Transformer is not there over here. A transformer is there in alternating current. Now, I'll tell you the manner in which they have explained. You might feel little bit confused. So I'll mark all the important pointers over here, of course. Electric current, okay, d phi by dt and all that. So important terminologies is term called as flux linkage, which is used to NB for a closely wound coil in such a case. The constant of proportionality is called as inductance. Okay, depends on the geometry of the coil and the material properties. Okay, the inductance is a scalar quantity. It has the dimensions of blah blah blah, given by the dimensions of flux by the dimensions of current. The SI unit of inductance is Henry. Okay, denoted by H. It is named in honor of. Okay, fine. And then there is another term called as mutual inductance, which long solenoids are there. Okay, the corresponding flux linkage is given by this. This is called as the mutual inductance of the solenoid. It is also referred to as the coefficient of mutual induction. The value of the mutual induction is given by this. Note that we neglected edge effects, blah blah blah. Okay, fine. Equality is very useful. Okay, and this is also there, mutual inductance. This is very important. And then they have also given this formula of the induced EMF in that coil, which is important. All right, and then they talk again about self-inductance, and E is LdI by dt, where it is also called as coefficient of self-inductance. Okay, and the energy stored is half Li square. Okay, and all these things. Okay, so now all these things, guys, I'll explain this to you in a very layman terms so that you understand, because the manner in which they have explained inductance, I really did not enjoy it. So it's better that you understand my explanation and then you can solve any question based out of it. Let's understand. Okay. Imagine there is a Pandu over here. Second case, there is a Pandu again over here. In the first case, there is a beautiful Champa in front of him. In the second case, there is no Champa for him. Champa tells Pandu, listen Pandu, you have to prepare for NEET. Listen Pandu, you have to become a doctor. Listen Pandu, if you become a doctor, I will marry you. Listen Pandu, you know, if you do well in life, I'll be with you. So Champa always keeps motivating Pandu. So Pandu studies for NEET, becomes a doctor. In the next case, no Champa is there. Pandu feels that I should become a doctor, automatically everything will fall in place. I have to do this, I want to work in this hospital, I want to go to AIIMS, I want to treat patients. In the first case, Pandu had some external agent to give that motivation. In this case, Pandu was self-motivated. This type of effect, in case of electromagnetism, is called self-induction. Here it is called mutual induction. Mutual induction. Self-induction is like self-motivation. Mutual induction is like mutual motivation. Mutually you motivated each other. When Champa motivated Pandu, Pandu was like, wait Champa, why you also come with me to AIIMS? Why only I should go? Champa is like, yeah, correct. I will also write NEET exam. So they mutually motivated each other. They both studied and they went to AIIMS. Understood, guys? Same thing happens. So this was your mutual motivation. Champa motivated Pandu. Pandu motivated Champa. Here, Pandu motivated himself. So this is basically your self-motivation. Okay, perfect. But in electromagnetism, it is slightly weird because of the sign, the direction of the current which is induced is always trying to oppose that change. So imagine it in a slightly different way. Instead of motivation, okay, I will call it the demotivation. It's like, you know, Champa tells Pandu, come, let's prepare for NEET. Pandu says, I will not prepare for NEET. And Pandu tells Champa, you also don't prepare for NEET. Champa says, no, I will prepare for NEET. So it will now become mutual demotivation. Here, in this case, just imagine Pandu tells himself, I have to go and play. All my friends are playing. Then he realizes, no, I should not play, I should study. His thoughts were saying something, but his ambition, his aim, his desire, his goal said another thing. So it was self-demotivating himself to go outside and play. Pandu knows that, okay, someday I have to sit and study, tomorrow exam is there. But Pandu is like, to hell with it, I will go outside and play. So he has demotivated himself for studies. So this is exactly what happens in current electricity, guys. Imagine you have a coil and you have another coil over here. This coil suddenly generates some magnetic field. If there is a magnetic field generated by this coil and it is changing, then it will create an electricity inside this coil. So there is an induced electricity in this coil to oppose this guy's change. If this is trying to increase, this guy will be like decrease. If this guy is trying to decrease the current, decrease the field, this guy will say, I will increase it. So it is like opposing it and it is generated mutually. That is why it is called as mutual induction. So this is the field This is usually called as the primary coil. This is usually called as the primary coil, and usually this is also called as the secondary coil. This is also called as the secondary coil. So the primary's field affects the secondary coil, and the secondary coil opposes the changes produced by the primary. That is your mutual induced phenomena. Is this absolutely clear? Absolutely clear, everyone? Hi Akhil, Warrior Pandu. Same way, over here, imagine only a single coil is there. Pavam, that single coil, was producing its own field. What happened? The current changed in it. The current changed in it. So the field also changed through that coil. Field either increased or decreased. That coil was there. Suddenly somebody turned on that knob or something, increased the voltage. The current increased. The coil is like, oh my god, current in my coil increased. So what should I do? What should I do? Faraday, Faraday, Faraday. Lens, lens, lens. Okay, okay, I have to create electricity. Okay, I have to oppose it. Okay, I will oppose it. Immediately it will oppose itself. So it will oppose its own change. That is basically your self-induction. There is only one single coil. So any change in the field produces an induced EMF induced in itself. Induced in itself. Here it is induced in the secondary. Here it is induced. Where is it induced? In the secondary. Is it absolutely clear? Everybody with me? The difference between self-induction and mutual induction. Very good. Awesomeness. Now, the formulas for each one of them. Observe it carefully. Observe it carefully. This is your secondary coil. This is your primary coil. The primary coil will produce some magnetic field. Maybe the magnetic field lines will go like this. Do you notice that not all the field lines are passing through the secondary coil? Only some of them are passing through the secondary coil. Can you see that? Only some of them are passing through the secondary coil. I hope you can see that very, very easily. Only some of them are passing through the secondary coil. If you bring this coil closer, or you increase the number of turns, or you basically put some iron core over here, then what will happen? The field will change, because iron core is ferromagnetic in nature, so it will increase the field. If I bring this coil closer here, those field lines which were being missed out, now even those field lines will pierce through the coil. If I increase the number of turns, the same field lines will pierce it again and again increasing the flux. So the flux which passes, the magnetic flux, the magnetic flux that passes through the secondary, coil, but generated by primary. Where is it generated from? The primary. Generated by the primary coil is called as the flux linkage. Is called as the flux linkage. I hope this is absolutely clear. This particular flux obviously is proportional to this particular flux which is generated in that secondary coil, right? This flux which is generated in that secondary coil is definitely proportional to the number of turns in the secondary, and also how much current is there in the primary. Basically, I will put it like this. It will definitely be proportional to the current in the primary. 1 stands for primary. If I increase the current here, more field will come. Obviously, more field lines will pass, so the flux will increase. Also, if I increase the number of turns in the secondary, so flux is directly proportional to the current as well as the number of turns in the secondary. Is this absolutely clear? Everybody understood this point? Great. Now, usually when we talk about flux, it's not through any one turn, it is the total flux. So obviously the total flux will be anyways proportional to the number of turns. Anyways, that is going to happen. So if I write that constant of proportionality as equal to, number of turns is a constant, I bring it inside, I just keep the current through the primary over here, this is flux through the secondary. Here, that constant which will come is called as mutual induction coefficient or mutual inductance. This is called as your mutual inductance. Very, very important. Mutual inductance. Is it absolutely clear, everyone? Everyone with me on this? Perfecto? Great. Now, a very important thing which you should know. You will be like, sir, here, this mutual inductance is when this coil is carrying current, producing field, and this coil is generating that electricity. What if I do the reverse? So very, very important statement which you should know. In the first case, this coil's field pierced through this. In the second case, this coil was generating. Okay, something like this. Here, this is primary. Now, this same coil became secondary. This coil was secondary. Here this became primary. If you ask me, in the first case, alright, the current through this coil is related to the flux in that second coil, given by this particular constant m. Phi is m into I. Flux in this is proportional to this current, and that constant of proportionality was called as mutual inductance. Now, if I do the reverse exactly, flux is passing through this coil labeled 1, coil which is labeled 1, this coil was labeled 2. This flux will be proportional to the current in this coil labeled 2. What will be that constant of proportionality? That will still be m. It doesn't matter which coil you make it as primary or secondary. Some books initially they refer mutual inductance of 2 with respect to 1. This is mutual inductance of 1 with respect to 2. So M12 is actually M21 is actually M. It is the same thing. So it doesn't matter which coil you make primary, which coil you make it secondary. It is always going to have the same constant of proportionality. Is this absolutely clear? That is what they have mentioned in one of the parts somewhere here. M12 is equal to M21. Okay? M12 is equal to M21. I hope this is absolutely clear, guys. Till this point, understood? Okay. Now, what does this mutual inductance depend on? Obviously, like I told, if I bring this coil close, far away, put some magnetic material, the flux will change. So it depends on the geometry, the shape, the size, distances, etc. shape, size, etc. It also depends on the materials which are placed inside. It also depends on the materials which are placed inside. It is also a scalar quantity. It is also very, very important. It is a scalar quantity. Not just that, if you talk about the unit part of it, this M is Weber divided by current. So a Weber divided by ampere is nothing but the unit of mutual inductance, which is basically Henry. H is the short symbol of it. Like Newton, you write N, same way, Henry is H. So 1 Henry of mutual inductance is when 1 ampere of current here produces a flux of 1 Weber over here. Then the mutual inductance is said to be 1 Henry. Is this clear, everyone? Awesome. Great. That was mutual inductance. Similarly, imagine a coil like this. Imagine a coil like this. The coil itself is carrying some current. That current itself is producing some magnetic field in it. So definitely there is some flux associated with it within itself. So the flux within a coil, due to its own magnetic field by the current, is again called as the flux linkage, is again called as the flux which has been linked, or the flux linkage. And this particular flux obviously is going to be proportional to the current passing through it. More current, more flux. Less current, less flux. Also, it also depends on one more thing, which is the number of turns. I have not shown over here. Obviously, it will depend. More turns, more flux. I into basically N. I into basically N. If you bring that N as a constant of proportionality and also more constants, whichever are there over here, I can write it as equal to, and then there is I, and that constant becomes as L. This is called as self-induction or coefficient of self-induction, self-inductance. Just like before, it again depends on geometry. More turns, radius, shape, etc. depends on geometry. It also depends on the material which is placed inside, and it is again a scalar quantity, and unit is again Henry. Same thing. Unit is again Henry. There is no difference there. So I need to block this. Phi is equal to Li. Till this point, absolutely clear? Everybody with me? Great. Now that you have understood till this point, what might be the self-induction of a solenoid? If you ask me, if I have a solenoid, just imagine like this. This is basically a solenoid. Okay, it is having some length L. Total number of turns is N. So N by L is small n, which is turns per unit length. What might be the self-inductance of a solenoid? How do I calculate it? Because a coil which is carrying current will be an inductor. This is an inductor. Inductor is basically the name given to this particular property of coils affecting each other or itself. That property is called as inductance when it affects itself or others. So how do I find that? Since there is only one coil, I need to somehow find the flux and show it is proportional to the current. Okay. So here is what I will do. The total flux in the solenoid, can I say it is n times the flux through each coil? N times the flux through each coil. N is the number of turns. Each turn will have some flux. So n times of that. What is the flux through each coil? It will be the magnetic field into the area of that particular coil into area of each turn. Correct? That's what it will be. And obviously cos 0, because magnetic field inside any turn of that particular solenoid, magnetic field inside any turn of that particular solenoid is parallel to the area vector of that coil. And this magnetic field inside a solenoid, we know the formula for it. It is nothing but mu naught number of turns into current, number of turns per unit length into current. We have seen this in the magnetism chapter. Oh, so I'll just put mu naught n I over here. This capital N is there, A is there, cos 0 is basically 1. So what I will do is I will write it as mu naught n. Okay, n, can I write it as small n into L? Definitely. Small n into L. This n is as it is, this I is as it is, this area is as it is. Rearranging it further, it will become mu naught n into n is n square, L A into current. Wow, perfect. This is the total flux. Can you see flux is directly proportional to the current? Flux is directly proportional to the current. When flux is proportional to the current, the constant becomes the inductance. Therefore, the self-inductance of a solenoid is mu naught n square length of the solenoid into area. Is this absolutely clear, my dear students, how we found this out? This is self-inductance of a solenoid. Self-inductance of a solenoid. How did we show it? By showing flux is proportional to the current. So whatever is there will be the self-inductance. Clear? Same way, we can go over here and we can find the mutual inductance of two concentric solenoids. Just imagine this. These are basically concentric solenoids. Concentric solenoids. The outer one, for example, I call it as the primary solenoid. That primary solenoid will generate its own magnetic field like this. And that magnetic field which is generated by the outer solenoid, magnetic field generated by our primary solenoid will be mu naught number of turns per unit length into the current passing through it, into basically the current which is passing through the primary coil, mu naught Ni, right? That is the magnetic field which is generated by it. But not all of that magnetic field passes through the inner solenoid. That outer solenoid is big. In that there is a concentric solenoid. Not all of it is associated for flux. If you notice very carefully, only a part of it, only a part of it is passing through the inner solenoid, which is our secondary solenoid. Inner solenoid, which is basically our secondary solenoid. So if you see the flux in the secondary, the total flux, is it not the number of turns of the secondary into the flux through each of the secondary coil? How much is that flux? It will be magnetic field which is passing into the area of that particular secondary coil into cos 0. Field into the area. Area is of this part. only this part, because I don't have to take the total area, only this area, because that is where the flux is passing in that secondary. Okay, so this is N2. What is B1? It is nothing but your mu naught N1, and you have your current, which is I1, and this A2 is as it is, cos 0 is 1. So therefore, the total flux will be, observe this carefully, mu naught is there, N2, I can do one thing, N2 by length is basically small n2. So therefore, capital N2 is L times of small n2. So L times of small n2, that is N2, then mu naught N1 is as it is, current 1 is as it is, and coming back to A2. So therefore, our flux will become, observe this carefully, mu naught, I have N1, I have N2, I have the length, I also have the area. The only thing which is outside is the current. Flux in the secondary is proportional to the current. Flux is proportional to the current. So whatever is there inside, what will that become? The moment flux is proportional to the current, the inside term will become mutual inductance. So mutual inductance will be mu naught N1, N2, length into area of the secondary coil. Very, very again important formula. This is exactly what they have derived over here also. If you see, no, these same things they have derived here. Mutual inductance, okay, self-inductance of a solenoid, all these things they have just basically derived the same thing. See, mu naught n square. Yeah, same things they have kept it. Okay guys, clear till this point? Mutual inductance formula, self-inductance formula for a solenoid. Okay, clear? Perfect. Now, one more thing which you should know. See, when these things are happening, when the flux in the secondary is mutual inductance into current in the primary, if I differentiate the left hand side and find the EMF in the secondary coil, which is minus d∅2 by dt, this is as per Faraday and Lenz, then this will become minus derivative of m into that particular current. But m is a constant, so bring it outside. So therefore, the EMF induced in the secondary will be negative m is there, and then you just have the derivative of the current. That's it. This is again an important formula to find the EMF. Just use Faraday's law. Differentiating flux, we get EMF. So EMF in the secondary coil is negative mutual inductance di by dt. Again, something which you should know. Definitely know. Same thing you can even do for the self-inductance, guys. Observe this now carefully. Because the flux in a coil is directly proportional to the current, the constant of proportionality being L. So the EMF induced in it, which is minus d∅ by dt, again this is as per Faraday and Lenz's law. So that EMF will become minus d by dt. We have that current and that self-inductance. L will go outside because it is a constant. So therefore, the EMF will become negative di by dt, and that self-inductance will just be over here. It's the same formula again. Instead of m di by dt, it will become minus L di by dt. Okay, this is the EMF which is generated in that particular coil. You should know one more thing. You should know one more thing though. The energy stored in an inductor carrying current is given by the energy which is stored is given by half inductance into current square. Very important formula. Half Li square is the energy which is stored inside that inductor. It's not difficult to remember it, like energy stored in a capacitor, half CV square. Instead of capacitance, you got inductance. Instead of voltage, you got current. Same, but different. Same, but different. Hi, Mrijesh Arvind. I'm so glad. I hope you enjoy all the classes and be very regular in the days to come. Bunny understood, very good. Yes, half Li square. Just to give you some simple examples so that you understand these formulas. If the current changes in a primary coil at 2 milliamperes per second, where mutual inductance is 0.5 Henry, then find the EMF and current in the secondary coil of 10 ohms. That's the question. There are two coils, that's why mutual inductance. Current is changing at a certain rate, so flux is changing, so electricity is produced. Mutual inductance is given to you, you have to find the EMF and the current. I just now told you, in order to find the EMF which is produced in a mutual case is given by m di by dt. You can see mutual inductance is given, the rate of change of current is given. We just have to find the magnitude of it. So the magnitude of the EMF produced will be m times di by dt. Mutual inductance clearly given as 0.5. Rate of change of current 2 milli. So 2 into 10 to the power minus 3 amperes per second. 2 into 0.5 is just 1. So 10 to the power minus 3 volts, or basically 1 millivolt, is the magnitude of the EMF which is being generated. If you ask me the current, that will be the EMF divided by the resistance of that coil. EMF is 1 millivolt, resistance is 10 ohms, so it will become 0.1 milliampere. That is the current produced. That is basically the current produced. Is that okay? That's how you solve this. Let's take another example. If an inductor stores 10 joules of energy for a current of 0.2 amperes, find the inductance and the flux which has been linked. Find the inductance as well as the flux which has been linked. Let's try to understand it. Because energy is involved, obviously we have to use half Li square formula. Okay, so energy is half Li square. But I don't know L. Maybe that's what we have to find. Okay, Is the energy given? Yes, 10 joules. Half is half. L, I don't know. Current, it is already given 0.2. So 0.2 square. So therefore, L will become 10 multiplied by 2 divided by 0.2 square, which is basically 0.2 into 0.2, which is actually 1 by 5 into 1 by 5. Is that right? 0.2 is nothing but 1 by 5. So 0.2 comes below. So 1 by 5 into 1 by 5. 10 2s are 20 into 5 into 5. That's what will happen when it goes on the top. So L will become 20 into 5, 100. Into 5, 500. So it will become 500 Henry. So that's the inductance. Job done. But there is one more question in this. The second part of the question says find the flux. The flux which is linked is L into I. Remember, Phi is Li. L, I already know, it is nothing but 500. Current, I think it was already given to me as 0.2, guys. Okay, so decimal goes inside, it will become 50 into 2. 50 into 2 is 100. So 100 Weber is the answer. 100 Weber is the answer. It's a very straightforward questions which are usually asked, so don't break your head too much. Very, very straightforward questions. Cool, guys? Okay, so that is inductors. Now the last part is AC generator, which we'll be talking about, and they have given the construction of the AC generator, and then they tell you how AC generator works, and there is a formula for that. Alternating current. So to show that, best thing to do is use the simulation. Now if you remember, just some time back when we started the discussions, I told you electricity is generated either by magnetic field changing, area changing or theta changing. Magnetic field changing, we did this problem where the magnetic field changed to 0 in this much time. You know, here angle changed or even the area vector can change. So, you know, this AC generator is actually a problem where you will see the angle between the area vector changes with the time in that field. Notice there is a coil. Notice that there is a beautiful coil over here. This coil has some area associated with it. This coil has some area associated with it. So this might be the area vector of that particular coil. This might be the area vector of that particular coil. Can you see some polarities? That is external bar magnet. Maybe there is a magnet which is placed like this, like a horseshoe magnet. Between those jaws or those clamps, you have a coil which can freely rotate. So definitely there is now a magnetic field which is involved over here. That magnetic field is, you know, over here like this. You can see that very easily. As the coil rotates, you can see with some angular speed, what will happen? The angle between area vector and magnetic field will keep changing. So at any instant, if you measure what is the flux, it will be B A cos theta. But there could be n number of terms, so n. So EMF, which is negative d phi by dt, will become negative derivative of this whole thing, which is B A cos theta into n. But many things are constants, like B is a constant, A is a constant, n is a constant. Only thing which will remain is derivative of cos theta with respect to time. But in circular motion, we have seen omega is the angle covered per unit time. So therefore, theta technically is omega t. So what I can do is, wherever that theta is there, instead of that theta, why not write it as omega into t? Now finding the derivative becomes slightly easy. So minus BAN, cos derivative is nothing but negative sign. So negative sine omega t, and that omega also comes outside. that omega also comes outside by ax plus b rule. Negative negative becomes positive, so it will become ba omega n sine omega t is the EMF generated. All these are constants, so I will write that constant as E naught sine omega t, where E naught is born, ba omega n. If you notice this carefully, you will realize this is a sine function. This is a sine function, guys. You know what it means? You know what it means? It means the EMF will go like a sine wave. Sometimes the current is clockwise, sometimes the current is anti-clockwise. So the direction of the current is sometimes positive, sometimes negative, means sometimes clockwise, sometimes anti-clockwise in the coil. So the current is alternatively changing the direction, hence it is called alternating current, AC current, the one which comes in your house to light up the fans, bulbs and the computers. So this is your AC generator working principle based on Faraday's and Lenz's law. Based on Faraday's and Lenz's law, the formula of the EMF is born sine omega t. Sine tells you it will become positive, negative, maximum, minimum, 0, maximum, minimum, alternatively changing the direction. The maximum value is E naught, that is the amplitude of the EMF, which is ba omega n. B is field, A is area of the coil, omega is the angular speed, n is the number of turns of the coil. Let's have a look at it. It's going to be beautiful. Wow, we have a tap. I can turn on the tap and I can see that this will rotate. I can see this bulb will probably light up. Are you ready for AC generator? Okay. Can you see? It is rotating it. Oops. It is rotating it. This is like a turbine. What is happening? This magnet is rotating, because of which in this coil, once the flux is increasing, decreasing. Well, increasing, the current is in one way, other time it is the other way. And slowly you can see the current is increasing, decreasing. EMF is increasing, decreasing. So that's what is happening. Can you see that? Let me increase the RPM. More water flows. Very quickly, dug, 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 it is rotating. The frequency has increased. I can increase the number of turns or decrease it. If I decrease the number of turns, you can see it very clearly here, the electricity produced is not so much. But if I increase the number of turns, the electricity produced is more, number of turns. Here number of turns is less. If I reduce the area, the light produced is less, electricity is less. Here, if I increase the area, the electricity produced is also more. So it shows it is proportional to area, proportional to the turns, also depends on omega and everything else. Yeah, so this is your AC generator. Such a beautiful, beautiful thing, isn't it? That is what has been exactly explained over here, and they have shown that same graph which I showed you. In fact, there is a problem also on this. I think this is on mutual inductance. Yeah, okay, fine, no problem. Two concentric coils, one of small radius R1 and another of large radius R2, such that R1 is much, much larger, coaxially obtain the mutual inductance. This is like your solenoid, but only one turn. No issues. We'll solve this, not a big deal. So there is a small coil here. R1 is the radius. And then there is a large coil over here. R2 is the radius, R2 is much, much larger. So that large coil might be carrying some current. Okay, let's say it is carrying some current I2. It will produce some magnetic field throughout. So some of the magnetic field lines will definitely pass even over here like this. That magnetic field is given by mu naught current divided by 2 times of the radius. Remember, that's the formula which you have seen in magnetism chapter. So obviously there is some magnetic flux which is associated over here. obviously there is some magnetic flux which is associated over here. So what is that flux? That flux in the secondary coil. Flux in that secondary coil. It will be magnetic field into the area of that coil. Area of that small coil is pi r1 square. So pi r1 square, I'll keep it here. What is the magnetic field? It is mu naught I2 divided by 2 times of R2. So that is your flux. What I will do, this flux I will write it as, this current I will separate it out, I2. The remaining terms which are there, I'll just keep it as it is, like mu naught pi r1 square by 2 times of R2. Can you see that the flux definitely is proportional to the current? So whatever is over here, that should be your mutual inductance. So mutual inductance is mu naught pi r1 square by 2 R2. That's it. That's the formula. Same thing. Mu naught pi r1 square by 2 R2. Same thing. What we have got over here. Always show the flux is proportional to the current. Your job is done. Whatever is the constant of proportionality becomes your mutual inductance. Becomes your mutual inductance. Okay. Great. So I think that was the last part of this, and this chapter is done, dusted. This lot of things are remember deleted from the syllabus of even mutual inductance. So all those things will also not come in the NEET paper. Hopefully, if it comes, it should be bonus. So just stick to the NCERT syllabus. That is what you should know. Earlier, when sometimes there used to be inductors combinations and then growth of current inside an inductor, LR circuits, LC oscillations, all those things used to be there, but right now those things are no longer a part of the syllabus. Okay, so just stick to whatever is there, don't break your head on that. Also, and new NCERT is the one which you should be following. Correct. Okay, have a great time, guys. Do not forget to like the video, and also remember all the details of all the syllabus is right over here in the description box. Some of you do not know this, so it's important for me to show. First of all, like, guys, what are you guys doing? Yeah, so you can see the complete treasure box is here. If you open the treasure box, right, it comes with the complete list of the chapters, the YouTube notes, the YouTube link of the video, the previous year test, the NCERT solutions if they are there, and it also is there for all subjects, physics, chemistry, biology. Okay, even the previous year papers links are there. All the study material is here for you, and the biggest test which is going to happen, which is the MVSAT link, is also here. Many of you have not yet registered. Please register right now because the exam is live right now, 10th to 20th October. So what are you waiting for? Quickly make sure that you are, oops, not the JEE Mains crash course. Why did this come? Yeah. Quickly take the test because there are a lot of prizes to be won, a lot of free goodies which will be given to you. And if you win the scholarship, well, all the courses come at a discounted price. Okay, you can use this even for our offline courses, be it in VLC centers, or even if you want to take any admission in our regular courses. So make sure you are writing that MVSAT. The exam is live right now. Okay, take care, guys. Bye bye. Have a great time. Captain Shreyas signing off. Hasta la vista.